Hi 7th grade Trailblazers. This video is for the week of November 2nd, so watch it and take notes because I will be looking at your notes in class. So let's get started. Alright, let's talk about energy and what it is, because that's the name of our game now. We're talking about energy and how it transforms throughout the universe, more specifically here on Earth. So first of all, energy is the ability to do work or cause change. So all objects have energy, and all objects exist in some state of matter. They're either solids, liquids, gases, or plasma. Okay, so a state, just so you know, is the form in which matter exists. So most matter on Earth exists either as a solid, a liquid, or a gas. We really don't have too much plasma here on Earth. That exists more in the universe. We do have it when lightning hits, though. So let's talk about when materials change state. And that happens when heat is added to a system. So what does that mean? It means that the molecules and the atoms, the atoms and the molecules, because they're getting heat, that increases their energy. So in turn, that increases the temperature. But when we take heat away from the system, the temperature decreases. If enough heat is added to or removed from a system, a substance in the system will change state. So let's talk about water. That's a good example. So if I put a pot of water on to boil and I increase the amount of energy by turning on the stove, and that energy is in the form of heat energy, and it's conducted to the metal of the pan, and then the water starts getting more of that heat energy. Those molecules, they're moving. They start moving faster and faster and faster because they have more energy until they reach the point where they actually change state from a liquid to a gas. The opposite of that is maybe I take an ice cube tray out and I fill it up with liquid water. I put it in the system. Heat is being removed from that water in the ice tray. And why is it being removed? Because heat always travels from something hot to less hot. So the actual heat in that water in that ice cube tray is traveling out to your freezer. Over time, that heat will dissipate, that energy will decrease, and that water will change state into a solid. So we know that solids have a definite shape and a definite volume. So think about an ice cube. It's a cube. If we got a ruler out and we were quick enough, we could measure its volume. And so they're very set in their ways. Even though their atoms are moving, they're moving at really low energy. Liquids are a little bit different. They have a little bit more energy, so they have a definite volume. Meaning if I have a can of soda, and it's 355 milliliters, and I dump it out on the ground, it's still 355 milliliters, but it doesn't have a shape of its own. So liquids take up whatever shape of the container they're in. Now gases are different. Gases have neither a definite shape nor a definite volume. So the gas that exists in a hairspray can will occupy that small volume and have the shape of the can, but immediately if I spray that hairspray, that gas spreads out until the molecules can spread out freely into the room it's being sprayed in, because that's the thing, they have high energy, they are excited, they want to move. Alright, so the change of state from a liquid to a solid is called freezing. So the temperature at which this happens is called the freezing point. The change of state from a liquid to a gas is called boiling, and the temperature at which it happens is called the boiling point. So some pretty easy definitions, should make total sense to you. All right, so how does this relate to energy? So we just said that from moving from all those states of matter, from solids to liquids, from liquids to solids, from liquids to gases, so on and so forth, we are adding or taking away energy. So when I talk about energy, there's two types. All forms of energy fall under the two categories, either potential or kinetic. So potential energy is the energy that results from the position or shape of an object, and we're going to talk about that in a minute. Kinetic energy is energy that results from the motion of an object. So when I talk about potential energy, I call that stored energy, and kinetic energy is the energy of motion. So let's talk about one type of energy. Mechanical energy is made up of potential and kinetic energy and is associated with the position, shape, or motion of an object. So when you're pedaling bike pedals, that is mechanical energy, okay? So that pedaling, your feet pedaling, moving the pedals, that's mechanical energy that is eventually going to move the bicycle. Next is thermal energy, and this is going to play into what we're talking about for a little while this term. Thermal energy is the total kinetic and potential energy of all particles. Okay, so all objects, everything consists of some thermal energy. Some have really low thermal energy, that's going to be my solids, and some are going to have really high thermal energy. That's going to be things like my gases. The transfer of thermal energy from a hot object to a cooler one is called heat. So when I talk about what heat is, I mean that transfer of energy from a hot object to a cooler one. All right, nuclear energy is a form of potential energy that is stored in the nucleus of an atom. Here in the United States, we do have some nuclear power plants, but they exist more in Europe. Americans are a little afraid of nuclear energy because they're very harmful if one of those power plants were to blow up. So what are we doing to use or harness the energy from atoms? We're actually splitting atoms, and we are harnessing the energy that exists, the potential energy that exists in the nucleus of an atom. So nuclear energy is only released during a nuclear reaction. Next is electrical energy. This is the electrons of an atom are able to generate an electrical current, and we call that electrical energy. And of course, electrical energy is what we rely on to power the world around us. We've talked about electromagnetic energy before, so you guys should know that it's a form of energy that travels through space in waves. And you know that's made up of really high frequency rays, like gamma radiation, to really low frequency waves, like radio waves. So energy increases as wavelength increases. Chemical energy, this is what fuels our body. So this is in the foods we eat or in the matches we use to light candles. It's potential energy stored in the bonds that atoms have together. So, for instance, water is made up of hydrogen and oxygen. That is a chemical bond that holds that molecule together. When I break that bond between hydrogen and oxygen, I release energy, and that energy is kinetic, and it is chemical energy. All right, so here's the deal here on Earth and in the universe. All forms of energy can be transformed into other forms of energy. So a change from one form of energy to another is called an energy transformation. So if I look here, I have my chemical energy, and it can be converted into mechanical, which can be converted into electrical, which can be converted into kinetic. I mean, we're always, the way the world works is this transformation of energy throughout our world. So we've got different types of transformations. The first is just a single transformation. This is just when one form of energy is transformed into another to do work. For instance, light energy from the sun, so visible light energy from the sun is used by the plants. They transform that light energy into chemical energy, and then we eat the carrot and we get that chemical energy, and we use it to do our work as humans. So when you are texting or you're on your computer right now and you're clicking buttons, that's all happening because the chemical energy in the food you ate is transformed into the mechanical energy your hands need to click the keyboard or whatnot. Most often, though, here on Earth, we need a series of transformations to do work. Let's use cars, for example. So in cars, we have an engine. So when you turn the ignition, in my car I don't have a key, I just press a button, but it's the same thing. What happens is a spark is going to be lit, and it releases chemical energy in the fuel. The fuel expands as it's broken down. So remember I talked about all those molecules, those atoms have stored energy. Remember, it's chemical energy. We're breaking those bonds to release that energy. The expansion of the fuel produces pressure on parts of the car. The increased pressure eventually causes the wheels to turn, transforming that chemical energy that was stored in the chemical bonds into gasoline. And what is gasoline? Remember, it's the decayed, old, dead dinosaurs that we harvest as oil to use as fuel, and we turn that chemical energy into mechanical energy, causing our cars to move. All right, the most common energy transformation is from potential to kinetic energy. So all objects have, they either at one point or another have one. So if I'm riding my bike up the hill, I'm in motion, I'm using kinetic energy. But when I get to the top of the hill and I'm not pedaling, I'm not doing anything, I'm just up there, for that brief second, that energy has been transformed from kinetic to potential. Now, the moment I start going down the hill, then I am using, again, kinetic energy. In a system, as energy is transformed, it is neither lost or created. Rather, energy is conserved. So this is a law. Get used to this, guys. There's a couple laws you're going to have to learn of in science. Remember, laws are things that can be observed time and time again. So the law says that energy cannot be created or destroyed. We can't create energy. What we can do is we can transform it from one type to another. So we can go from chemical to mechanical, we can go from electrical to mechanical, so on and so forth. We are just always transforming it. We're never creating or destroying it. So friction's pretty cool. It's a force that one surface exerts on another surface when two surfaces rub against each other. So in my picture, I've got a car. So I've got this wheel spinning, and then I've got the ground. Now, friction is the force that occurs when these two surfaces meet. And what happens is when parts of this wheel are hitting friction from the road, some of the kinetic energy is transformed into heat. So 9 times out of 10, when I'm doing energy transformations, I don't get 100% of that energy changed from chemical to mechanical. I lose some as heat or thermal energies. So that's always a byproduct. Think of a lamp. A lamp is converting chemical energy into light energy. However, if you leave a lamp on long enough, does all of that chemical energy get transferred into light energy? And your answer would be no, because if you've ever touched a hot light bulb or touched the light bulb after the light's been on, you know it's hot. Why? Because some of that energy is lost as heat. Not lost, I should say transferred to heat. So the energy of a system that is exposed to friction may decrease. But overall, this shows that energy in a system is not lost nor created. The heat is just evidence that we are conserving energy, that we don't destroy it, we're not making it. Most of it's transferred to the other form, but some of it's lost as heat. Alright, and I've got a video for you. Let me get rid of my laser pointer here so I can start this video. Alright.
Energy is not easy to define. Things have energy, but you can't hold a bushel of energy in your hands. You can see what it does, but you can't see it directly. There are different types of energy, but the differences between them are manifested only in how they make stuff behave. We do know that the total amount of all the different types of energy in the universe is always the same. Now, for chemists, 2 important types of energy are chemical potential energy and kinetic energy. Potential energy is energy waiting to happen. Think of a stretched rubber band. If you cut it, all that potential energy gets converted to kinetic energy, which is registered by you as pain. Like a stretched rubber band, chemical bonds also store energy, and when those bonds are broken, that potential energy gets converted to other types of energy, like heat or light, or gets used to make different bonds. Kinetic energy is the energy of motion. Now, molecules are always moving. They're not necessarily going somewhere, though they could be. But they are vibrating, stretching, bending, and or spinning. Take methane, which is 4 hydrogens attached to a central carbon, as an example. Drawn on paper, it's just a still tetrahedron. But in real life, it's a jiggling mess. The kinetic energy of molecules is exactly the same type of energy as the energy you have when you're moving around, except that you can be still, and molecules can't. If you suck the kinetic energy out of a group of molecules, they'll move less, but they'll never fully stop. Now, in any group of molecules, some will have more kinetic energy than others, and if we calculate the average kinetic energy of the group, we'd have a number mathematically related to temperature. So the more kinetic energy a group of molecules has, the higher its temperature. And that means that on a hot day, the molecules in the air around you are spinning, stretching, bending, and generally shooting around much faster than on a cold day. Now, hot and cold, by the way, are relative terms. They're always used to compare one thing to something else. So on that hot summer day, the air molecules have more kinetic energy than the molecules in your skin. So when those air molecules crash into you, they transfer some of their energy to the molecules in your skin, and you feel that as heat. On a cold day, The air molecules have less kinetic energy than the molecules in your skin, so when you crash into those air molecules, you actually transfer some of your kinetic energy to them, and you feel that as cold. You can trace the path of energy around you. Try it at your next cookout. You burn charcoal, and the release of that chemical potential energy shows up as extreme heat and light. The heat then makes the molecules of your burgers, your hot dogs, or your vegetables vibrate until their own bonds break and new chemical structures are formed. Too much heat and you have a charred mess. Just enough and you have dinner. Once in your body, the food molecules in your delicious or charred dinner get broken down, and the energy released is used to either keep you alive right now, or it's stored for later in different molecules. As night falls, the hot summer air cools, and the flow of energy into you slows. Then, as the air reaches your skin temperature, for the briefest of moments the flow stops. And then it starts up again in the opposite direction as energy leaves the warmer surface of your skin to return to the universe around you. That energy neither created nor destroyed, but ever shape-shifting, the chameleon phoenix of our physical world.
All right, my darlings, I will see you in class. Have a wonderful week.